We have Professor Jia today with us from the University of Michigan and the Climate and Space Sciences Department in the College of Engineering. He is a specialist in understanding planetary and lunar moon magnetospheres as they move through their own planet's environments with a number of different kinds of impressive simulations that we're going to see today. You've been at Michigan since 2009, I think.
Yes.
And was a NASA early career fellow back in 2016. So without further ado, let's go ahead with your talk. Thank you very much.
Thank you, Chris, for that kind introduction, and also for inviting me to be here visiting you guys. I had a lot of very good, productive interactions, conversations with some of you throughout today. And as Chris mentioned, my research interest has been planetary magnetospheres and planetary moons, especially their magnetic properties, interior structures, and how they interact with their parent magnetospheres. Today in this talk, what I'm going to talk about is some latest development and efforts we have been working on in the last 5 or even 10 years. You know, when I go through the slides, you will realize a lot of these have started 10 years ago, and basically coming up with a new modeling approach that could allow us to capture important kinetic effects in a global setting. I'll explain what that means in the following slides. And the image I put up here is a snapshot from a recent paper we published maybe 2 years ago for the magnetosphere of Mercury, the smallest planet in our solar system. And the thing we try to highlight in this type of illustration is these flux slope that is frequently observed by the MESSENGER spacecraft. And now we're able to reproduce the formation of those flux slopes in our global simulations. And I talk about a lot of details about the work later on, but this is going to be the focus of my presentation today. But before I go into that, I do want to acknowledge that a lot of this work is done in collaboration with my students, current students, 2 of them working now in my group, and former students who graduated a couple of years ago, and also with our code developers at University of Michigan, especially Dr. Xianzhe and a couple of Toth, who have long been investing in developing the MHD and with coupled particle in cell code that I will be discussing today. I thought it would be interesting, useful to talk a little bit more in general terms when it comes to modeling planetary environments. And a lot of these are actually applicable to solar terrestrial environment as well. So, and that's basically the work I have been doing over the last 16, 20 years, since I was a PhD student even. So when you think about simulating planetary environments, these are things I often pay attention to. For example, interaction between plasma and neutral particles. And you see this type of interaction in many different environments, cometary environments. You have a lot of neutrals being released from the nucleus, and when they become ionized, they start to reactions between each other, and they can influence the electromagnetic fields. And we see that also in planetary environments as well. If you think about the giant planets, Jupiter and Saturn, those magnetospheres, their plasma sources come primarily from inside, from their moons. Io in the case of Jupiter, Enceladus in the case of Saturn. And there is going to be a constant mass and momentum loading that will be imposed onto the magnetosphere whenever you produce a neutral particle and some of the neutral particles are being ionized. This will create mass loading. And if you do charge exchange between neutrals and charged particles, this leads to momentum loading, okay? So, and more complicated, a lot of complications come when you deal with multi-species environment, which is the case for both the Saturnian and the Jovian magnetospheres. And the materials that are coming off of those moons are going to be composed of molecules and when ionized, producing a lot of daughter species. So the plasma environment in those magnetospheres truly is multi-species environment. So there we see a lot of needs or demands in order to properly model that kind of interaction. You have to somehow incorporate this important physics into your global modeling. So that is what way I deem one critical aspect, to handle the plasma neutral interaction. And many of the planets and some of the moons, they even possess ionosphere. So there's a lot of interesting work done here in this department in terms of the coupling between the ionosphere and the upper atmosphere for different planets. And I had a lot of interesting discussion with Tommy this morning about the work that his group has been doing. And the ionosphere is a very important part of the global magnetosphere system in the sense that it electrodynamically coupled to the magnetosphere through currents, electric fields, and sometimes through material exchange by ionospheric outflow. So again, these are important processes that also need to be taken into account if you're modeling a planetary environment that has an ionosphere. So the magnetosphere-ionosphere coupling is, again, a crucial aspect. Now, in recent years, as we start thinking about exploring planetary objects that have very strange or very special interior structures, we realize that coupling to the ionosphere itself is not enough. You somehow have to extend your simulation even below the surface into the interior. And I'll give you a couple of examples. The two examples I'm going to talk about at length today, Mercury and Ganymede, both of these objects have very interesting interior properties. Now, Mercury has a very large size conducting core. The core is 80% of its radius. Now, when you think about this, Earth is a magnetized planet as well, but Earth's core, the outer core, is only 40% of the radius. So even though the Earth has a very strong dynamo producing magnetic field, the core itself is relatively small in comparison to the size of the planet and in the comparison to the size of the magnetosphere Earth has. But Mercury is in a different regime. The core is so close to its surface and also so close to its magnetopause boundary. There is a very strong feedback between the magnetospheric environment and the core itself through the so-called induction process. So whenever the magnetosphere is changing its size, shrinking, expanding, the core would respond electrodynamically by producing eddy currents flowing at the outer edge of the core, and that currents produce additional magnetic perturbation. So that is very important physics we need to take into account if we want to properly model Mercury's magnetospheric response to solar wind driving. We see other similar environments like Jupiter's moon Europa and Ganymede. And these moons have been suggested to host subsurface oceans. Ocean that is the melted ice with some salinity, with some salts embedded, such that those oceans become conductive. And that is very basis that some of the missions that we now have, Europa Clipper and JUICE missions, are going to rely on in terms of understanding its interior structure. But again, these subsurface oceans produce the induction effect, and that will in turn influence its spacing environment through generating additional magnetic fields. So you have to include that into your global modeling if you want to have a good handle on understanding or retrieving the induced magnetic field. So in recent years, we have actually made a lot of efforts trying to incorporate subsurface properties, interior structures into our global model, so we can have a self-consistent simulation of the response of these planetary bodies to external forcing. And the last aspect I want to talk about briefly here is the kinetic effects. As many of you know in this room, I'm sure it's through my conversations with you this morning, a lot of you are doing a lot of interesting physics with particularly focus on kinetic effects, wave-particle interactions, and magnetic reconnection. Now, from the perspective of planetary magnetosphere modeling, magnetic reconnection has always been a very important element. But we all know, traditional approach using MHD has a lot of limitations, especially when it comes to simulating magnetic reconnection. you either have to rely on purely numerical effects to get reconnection start, or you have to rely on anomalous ad hoc resistivity, for example, you add to the model to initiate fast reconnection. So we try to take a different approach in the work I'm going to talk about today, is to couple MHD models with a kinetic model, such that the regions where reconnection or other potentially important kinetic effects are present is going to be handled by a fully kinetic code particle in cell. And the rest of your simulation of the global system will then be handled still by MHD. Okay, so that's the basic concept here, which I will explain in a few slides. And once you have that kind of modeling capability, you can start looking at various kinds of interesting physics then, particle transport, ionization, distribution functions, how they deviate from your Maxwellian distribution you start with. So this is going to be my focus today. And I'm going to, as I mentioned in the presentation title, I'm going to use Mercury and Ganymede, these two objects, as an example to illustrate this relatively new modeling approach we call MHD EPIC model, which stands for MHD with embedded particle in cell approach. So let's go to Mercury first. A very quick introduction of Mercury, just in case that you are not very familiar with this environment. Now, this is the innermost planet and the smallest in our solar system. It's located somewhere between, on average, 0.4 AU distance from the sun. And NASA had a few spacecraft that have visited Mercury, but most recently it's the Messenger spacecraft that spent 4 years orbiting Mercury. That really taught us a lot about what this environment operates, how this environment operates. Now, this is a schematic diagram that tries to illustrate the important dynamics and the structures that you see in this relatively small magnetosphere. Now, the thing I will be focusing on is these flux-like structures that are formed very frequently on the magnetopause, the boundary that separates Mercury's magnetosphere from the solar wind. And when Messenger got in and orbiting for 4 years, it detected a large number of these called flux transfer events, FTEs. Now, essentially, I think people studying different parts of the space environment would come across different names for the same flux-like structures. And people sometimes call these fluxual plasmoids if they appear in the magnetotail. You see that here in this diagram as well. If it appears in the magnetotail, we often call it plasmoid. If it appears on the magnetopause, we often call it FTEs, flux transfer events. And this is because of the history, I think, when these things first being discovered. But in any case, these are product of magnetic reconnection, for sure. So when you observe this, and one of the nice things about the FTEs is that it is relatively easy to discern, to identify and measure based on magnetic field measurements. You do not necessarily have to have plasma measurements, which always is a challenge when you go to the planetary environment to obtain. So that actually makes these FTEs particularly important because you can see them relatively easily in the magnetometer data. Okay, and you can construct large statistics to understand their occurrence frequency and under which conditions they appear more often than in other times. Okay, so the FTEs have been observed very often at Mercury, and when you look at it in a more detailed sense in terms of their dependence on the ambient external conditions, namely the solar wind and in the planetary magnetic field, what's even more surprising here is that what the Messenger showed is it seems like the occurrence of magnetic reconnection at Mercury does not really care very sensitively about the orientation of the ion. Now, conventionally, we often invoke so-called anti-parallel reconnection to be the canonical picture in which we kind of see reconnection happening. But we also know there's component reconnection that could also, in principle, happen when you have a finite shear between magnetic fields on the two sides of a current sheet. And what's surprising at the Mercury is the FTEs and other reconnection products are seen over a very wide range of magnetic shear angle. Sometimes even when the magnetic field are almost parallel to each other, you still see formation of the so-called FTEs on the magnetopause boundary, which is quite surprising. Now, the the mechanism that the interpretation that's been put forward has been largely relying on the so-called low alpha-anic Mach number solar wind that Mercury routinely experiences in the inner heliosphere. Because there is indeed the Mach number of the solar wind at Mercury's orbit is somewhere between 2 to 4. And when you move out to the Earth's orbit, it becomes 8 to 10. When you go to giant planets, is way above 10. So the Mach number of the solar wind, the alpha-anic Mach number, goes up almost monotonically all the way up to the major planets we see in the solar system. And that does provide a plausible explanation because the solar wind plasma conditions are quite different at Mercury. And the plasma beta across the shock in the Mercury case becomes comparable, or it becomes relatively small in comparison to the plasma beta inside of the magnetosphere of Mercury. So there's not a big difference in terms of beta conditions across the magnetosphere boundary. And in that regime, reconnection seems to be able to take place, even if you have a very small shear angle. If the delta beta, if the beta conditions are quite different between the two sides, then reconnection is largely suppressed for small shear configurations, but it's only gonna be active under very large shear conditions. So that was the kind of, I think, what the messenger had shown, at least from the observational standing point of view. And this is, at the bottom is just the example from messenger observations where you can see all these spikes and dips, and all these have been identified as so-called FTEs. So each one of these blue arrows represent a flux slope that has been identified in the messenger magnetometer data. And when you see so many of them, the messenger team even tagged this with a term called FTE shower. So it's a shower event. There are so many. The separation, the average separation between the neighboring events is only a couple of seconds. So in other words, every few seconds, you see an FTE coming up, every few seconds. Now, to put things into context, at Earth, the canonical number we quote is 8 minutes. Is every few minutes also, you see an FTE event happening on the Earth's magnetosphere. But yes, of course, you could argue the Earth's magnetosphere is much larger in size than Mercury's. Of course, that is true. But even if you take that scaling into account, and that scaling factor is often number we quote a factor of 8, it does not explain this 2 seconds and 8 minute difference that we see in the FTE occurrence. So the modeling work we've done, especially by my former student, is trying to see in the global simulation, first of all, can we reproduce the formation of the FTEs? And if we can we look at the dependence of the FTE properties on the various external parameters, solar wind, for example, solar wind Mach number, and the IMF strength and orientation. So what we decided to do first is we want to do 2 sets of simulations. One is we want to approach this with a relatively simple approach. We use so-called the Hall MHD approach before we even get into the MHD with coupled pit, because we want to know in the fluid treatment how well or maybe how poorly you can simulate structures like the FTEs that I showed you in the previous slide. And in fact, even 20 years ago, the GEM community, the geospace environment community, had this famous GEM challenge on magnetic reconnection, looking at different models containing different physics and how different, how similar they are in terms of capturing magnetic reconnection. And one of the, I think, very important results from that effort was found is the Hall MHD seems to be the cheapest modification that you may want to implement if you want to really capture fast reconnection, this canonical 0.1 reconnection rate. If you simply say, I want to still stay within the fluid treatment, but I want to capture this fast reconnection. So going beyond the single fluid ideal MHD to Hall MHD seems to be able to give you that once you start allowing separate motion of ions and electrons into the diffusion region. So that's why we decided to try Hall MHD first within our BATS-RS MHD code developed at Michigan, part of the space weather modeling framework. And the setup is relatively straightforward. But one key thing I want to emphasize is to really resolve the Hall effect, you have to go down in resolution to below the ion neutral length Okay, so the grid resolution we have placed near the upstream magnetopause is 20 kilometers, which is about 1/6 of ion inertial length in that region. That means we have 6 grid points for 1 ion inertial length. Okay, that is perhaps reasonably good to capture the ion scale. And we also, in this simulations, in the following simulations I'm going to show you, we include the planetary interior of Mercury. So as one thing you can tell you is, this surface is the planetary surface, that's the yellow circle, and this black disk is representing Mercury's core. And you can see the magnetic lines go all the way inside. Instead of traditional models will stop their calculation above the surface. And we now evolve the magnetic diffusion region inside of the planet for a prescribed conductivity profile based on geophysical measurements. So we can prescribe the conductivity high and low corresponding to mantle, corresponding to core, so that when you drive the system, magnetic induction will happen naturally and self-consistently, depending on the conductivity profile we have imposed in the simulation, okay? So, and this is one animation I want to show as a demonstration of the simulation results. And here you can see, as soon as you allow the simulation to proceed, you see all these formation of island-like structure in this cut plane, and that is the FTEs that we've seen in the data along the spacecraft track. But in the full 2D sense, you see these islands popping up very frequently, and sometimes you see a few of those showing up at one snapshot. And as soon as they're born, they're going to move either northward or southward, depending on the competition between neighboring X lines that are formed, and they're going to evolve and expand, interacting with the surrounding media. Some of the FTEs will get dissipated as they cross the cusp region through so-called reconnection. Okay, so for the whole image simulations, when my student decided to run for 6 different scenarios that cover 2 Mach number regimes, Mach number 2, very low Mach number, and Mach number 6, the higher end of the Mach number is being observed. And also for each Mach number case, he tried different IMF orientation. Okay, and the parallel and 90 degrees orthogonal case and the 135 intermediate case between the IMF and the Mercury's magnetic field. So very quickly here, if you look at one of these FTEs, clearly you can see they show up as a flux rope structure, right? It's looped up and they have a very strong core field in this particular example. And so everything looks good on that chart, but things become very quickly complicated in the sense that when you see so many FTEs, how do you analyze them? Okay, we have to find a way to capture them and then to extract useful information out of the simulation. So this is, again, kind of a series of snapshots trying to show the evolution of FTEs. Sometimes you see merging of these islands between 2 small ones evolving into a big one. And also this gives you a sense of how frequently you see these FTEs. If you see this first snapshot, we have 5 islands identified. We label them F1 to F5. Towards the end of the simulation, each panel is separated by 2 seconds. Towards the end, we have F9, okay? So in this 14 seconds, we have 4 new FTEs generated. That gives you a sense of time scale. In 14 seconds, we see 4 new FTEs. So on average, every 2 or 3 seconds, we see a new FTE on this magnetopause. So then we spend a lot of time actually thinking about how we're going to do the identification of FTEs. So when you look at the cut like this, you can figure out the boundary of the magnetopause, and you see these islands. So it's a matter of extracting these islands out and then extracting other properties like density, magnetic flux content, and how fast things move along the magnetopause boundary. So we did all that, and one of the useful ways I really like is this kind of people studying solar physics has this equivalent butterfly diagram. When you look at sunspot numbers, as function of time, we have kind of reversed diagram of that version. So basically these are, if you cut you make a model for the magnetopause and you start extracting all the relevant parameters along the magnetopause boundary and watch how they evolve in time and in latitude. And these colors here on the top panel shows the normal component of the magnetic field, normal to the magnetopause boundary. So if an island shows up, you would expect the structure comes with a pair of positive and negative BN. Okay, so that is what you can see here. For example, this one, you have a red band, you have a blue band. And the center of that is the core, the center of the FTE. So that's the way we kind of pattern recognition technique try to identify all these structures. So there's all these magenta dots are the centers of the FTEs that we have identified. Each one of these corresponding to the center of blue and red pair of BN. Okay, and the bottom panel shows the same results, except that the colors here now showing the core field, the axial component of the magnetic field. What you can see clearly here is the center of the FTEs most of the time corresponds to a strong core field. And that's the very exact symptom of the flux robe. Near the center of the core, you expect to see very strong core field. So these are truly flux robe-like structures formed in the magnetopause. And also by looking at the slope, you can estimate the speed at which these FTEs move in time. And they're not uniform. Sometimes they start out slowly, but then they suddenly accelerated north and south.
What's the difference between the magenta and black dots?
That's a good question. I think the black dots, if I remember, is what we call the flow stagnation point. So we're trying to look at the magnetic separatrix and the flow stagnation point, which do not necessarily have to overlap. Mm-hmm. So I think that was that attempt trying to compare the two.
Okay.
Thanks. And once you have that kind of butterfly diagram, we can start constructing statistics. Right? Now we have a way of knowing where FTEs are, and we can then go ahead and extract the size of FTEs in both dimensions. It's a semi-axis length. So we can do that, and looking at, for example, FTE size, we can construct the statistical diagram, histograms of the FTEs that we see in all these simulations. And this is only one comparison that we published 2 years ago, showing the two Mach numbers, and you can clearly see the differences. In one case, in the low Mach number case, we see FTE size is relatively smaller, but happens more frequently. So in the low Mach number case, we see more frequent occurrence of FTEs, but with relatively small size. When you go to higher Mach number, and you see a larger FTEs form, but they form less frequently, okay? And there are other things I don't have time to talk about in this presentation, but we did a lot of comparison for different, not only for the Mach number case, but we also compared for different IMF orientation, trying to get a sense of how the properties of FTEs depend on these external conditions. Now, after that is done, what we're interested is, now since we have this MHD EPIC model available in-house, can we use that, we think, a better physics model to do the same experiment? So very quickly, I want to explain what this model really is about. From name, you can tell we want to embed particle in cell inside of MHD code. Now, MHD is well known for its efficiency, and we can do global simulations fairly fast with MHD models, but it does not contain kinetic effects, does not contain kinetic physics. If you want to model reconnection, well, MHD really is not the approach to go to in this case. So we want to rely on a kinetic code to handle reconnection. And we started out 10 years ago in 2014, we started coupling the BATS-RS code, MHD code, with the IPIC 3D implicit particle in cell code provided by Johnny LaPenda and Stefano Makidis. And now in the recent several years, we start developing our own particle in cell code now called Flex. Okay, and it's a semi-implicit particle in cell code. And these two codes are coupled in a two-way fashion. And this diagram flowchart indicates that. So we initialize the system, we run the MHD model for the entire domain that covers whatever system you're interested in, for example, Mercury's magnetosphere. So we run an MHD model for the entire magnetosphere domain. But then as a user, you can specify regions where you want to place the PIC code. Okay, that's customizable. You can specify that in the input file. And then the two code would run on their own, but they're gonna talk with each other at a specified cadence. Okay, so that's every second. The PIC code will talk to the MHD code and vice versa. And the information they're gonna exchange at that cadence is boundary conditions. Okay, so the MHD code provides boundary conditions to the PIC. And the PIC would run on its own, solving kinetic ions and the kinetic electrons, and then produce moments. And those moments, plasma density, bulk velocity, and temperature, will then be overwritten back to the MHD domain. So the MHD domain gets update from the PIC at these specified cadence. Okay, now you notice that these two codes, they're written totally different design. They do not have to have the same time step. So you have to do some timing, to allow them to communicate in physical time. So every delta t, they're gonna talk to each other. Now, all these is done within our space weather modeling framework that has a long history at Michigan. And we use two-way coupler, and this will allow us to do this fairly efficiently. And recently with the Flex, we're now able to, we used to be able to only use Cartesian grid and Cartesian box to specify the PIC region. But we realized when you do magnetospheric simulation, and if you want to be more efficient computationally, Cartesian box may not be the best choice, because if you look at the shape of the magnetopause, if you want to cover the entire magnetopause, you have to use a very big box, and that box eventually become the whole magnetosphere. So the very idea of the so-called Flex is to allow us to use a custom designed outer boundary of the PIC. In other words, you can, as a user, specify whatever shape you like for the PIC domain. And I'll show you an example on the next slide. So when my students start looking into this, he said, okay, if I look at the MHD simulation results in terms of the magnetosphere, this is in the meridional cut. And this is the MHD grid, which itself comes with multiple level of mesh refinement. You notice that we have a very refined grid near the magnetopause. And what he did then is he specified functions to construct this PIC grid, which is highlighted by this black curve. And as you can notice, it's nowhere close to a rectangular box. It's highly curved and follows largely the shape of the magnetopause. It's basically a parabolic function that we specified inside the code. So now this region confined by the black curve is solving kinetic ions and kinetic electrons entirely inside the code PIC region, and everywhere else is being handled by Hall MHD. Okay, and it has a very nice, we purposely stay away from the surface of Mercury, so this black boundary is just 2 grid points above the surface. But everything is made possible by this new capability offered by Flex. For those of you who are very interested in PIC simulations, we use a mass ratio of 100 for ions and electrons, and 128 macroparticles for ions and 128 for electrons. We have 256 particles in total inside of a cell. We try to use similar resolution to enable a apples to apples comparison with our Hall MHD simulation. Very quickly, if you look at some of the distribution functions now we're able to obtain from the PIC simulation, which are shown here on the right. And this may not be very clear on this projection, but this is an example where we sample the distribution function very close to a reconnection X line, okay? And this is the ion distribution function, this is the electron distribution function, and projected onto the plane that's perpendicular to the magnetic field and the planes that are parallel to the magnetic field and electric field, convectional electric field coordinates, okay? And here you might notice some familiar structures like you often see close to reconnection sites, like this one is crescent shape distribution. You get a core distribution, but you get this crescent distribution showing up slightly away from the origin. And when you look at the electron distributions, it shows up, in this case, highly anisotropic with parallel direction temperature much higher than the spread in the perpendicular direction. Okay, so this is an example that we extracted from very close to a reconnection X line. If you look at another example here, I apologize for the color choice here, but this is the sampling point we placed in the southern cusp region of the magnetosphere. And again, ion distribution and electron distribution. And if you look at the ion distribution, you see this two kind of a beam-like, it's not entirely a beam, but streaming population along the magnetic field line. So we're seeing the ions going downward, precipitating into the cusp, and we're seeing a fraction of those particles being mirrored back up by the stronger magnetic field near the surface and backing up. So we see this counter-streaming particle populations in the ion distribution. And surprisingly, in this case, the electron distribution seems more or less isentropic as they evolve into the cusp region. So I think this gives you a glimpse of what the PIC model is able to offer. And there's a large amount of information contained in the output. And still nowadays, we're spending time kind of digging into the output and trying to understand the implications from these PIC simulations. Now, this is another example from the particle in cell output, where we use that as a way to identify the mechanism that's producing these for FTEs. Now, these field lines are the black lines, and the isosurface showing you density, high density regions, which are inside of the flux rope. And these red dots are the region where we have identified that contain non-MHD electric fields, or the non-MHD electric field had exceeded a certain threshold, and those are depicted by these red dots. Okay, so that gives you an indication where reconnection has happened in that frame, and you can tell that these FTEs often form between, they're sandwiched by these X lines. Okay, so that is giving us a very strong indication that these FTEs is a result of a so-called multiple X line reconnection. So you have one maybe X line happening initiated first, and another one at another location, and those reconnection product would give rise to these flux rope FTEs. And you can follow them in time, and you can see how things evolve and distorted by, sometimes we see these FTEs first form as a horizontal structure, but later they become highly extended. And that's because you get another reconnection site happening somewhere below these in one hemisphere, and that sort of the outflow of that X-line reconnection sort of pushed the flux loop into an orientation now becoming more or less orthogonal to the equatorial plane. So that, I think, is the kind of the quote unquote turbulent nature of the reconnection happening on the magnetopause that give you all these kind of very dynamic and strange distribution of FTEs on the surface of the magnetopause. And then from that, you can go one step further and doing counting the probability of seeing reconnection happening on the magnetopause. And this is a map that we have constructed for 2 different Mach numbers and the 3 different IMF orientations. So we have 6 maps. Now, I don't have time to explain all of these, but I think one general trend that we have noticed is these numbers here showing you probability of seeing a reconnection event in 1/2 of this hemisphere. Either on the left is the dawn side of the magnetopause, and this is the dusk side. And we see a persistent pattern of asymmetry that reconnection tends to happen more frequently on the dawn side in comparison to the dusk side. The probability is always higher on the left-hand side of this diagram than on the right-hand side half of that. And in the past, people have looked at mechanisms like X-line spreading, which would promote asymmetry towards dawn, and the suppression of reconnection due to Hall effects, which would also promote asymmetry towards dawn. And I think we're at least now in the simulation, we're seeing the trend consistent with these predictions that are made in previous work in the more localized reconnection box studies. But we're seeing similar patterns here now in the global setting and in a more realistic setting where you have a dipole magnetic field inside and IMF, shocked IMF coming from outside. And we're seeing similar asymmetries as predicted by previous reconnection studies. And maybe both of these effects act together to produce this very obvious dawn-dusk asymmetry we see in the Mercury simulation. And I have time to talk about this chart. I mean, it requires a few minutes to really discuss this, but these are the dependencies of FTE, simulated FTE properties as a function of Mach number and as a function of IMF orientation. And we also compared the results between the Hall MHD and the MHD epic. Now, I do want to spend a couple of minutes talking about this very new work that my current student Alex is doing at Michigan. You know, the previous work is focused on the day side, the FTEs, and he's interested in the night side dynamics. He wants to know, because also Messenger had shown there's a lot of interesting things happening on the night side in the magnetotail, formation of flux rope or plasmoids, we call it, and the dipolarization fronts forming and the electron energization on the night side. And again, one of the biggest mysteries left by the Messenger mission is there's a very strong dawn-dusk asymmetry on the night side in terms of reconnection-driven dynamics. For example, energetic electrons are mostly seen on the downside. Very little events are seen on the other side. And reconnection products, dipolarization fronts, everything seems to be favoring the downside magnetotail. So we want to have a good understanding of why that's the case. So what he did is he's trying to place the pick box on the night side, and on the right-hand side, if I play the movie, so he's done a quite interesting analysis here. He's extracting the current sheet. So you see this wavy isocircuit that shows you the current sheet in the simulation as a function of time, and the colors of that isosurface shows you the delta BZ, okay, the perturbation magnetic field normal to the current sheet. And all these blobs, green blobs, are structures that have delta BZ exceeding 10 nanotesla in the tail, okay? So let me play this movie, and you can see the whole magnetotail never had a quiescent time. It's always dynamic, and you have reconnection happening almost all the time. And you see these green blobs. And these are what he had assigned as dipolarization fronts in the magnetotail. And once they form more or less evenly across the magnetotail between dawn and dusk, but as soon as they form being transported towards the planet, which is here, they go towards one side. They all go towards the dawn side, which is the right-hand side, right-hand half of this domain. And so that is, again, consistent with observations, but we're trying to figure out, you know, what is the physics behind this? Why the structures, once they form, they favor moving towards one direction. Before you can do that, you have to sort of, again, just like the FTE things that we talk about, you have to have a way to track these structures, dipolarization fronts. So he had to develop yet another scheme to automate this tracking. Again, I don't have time to explain all of this, but what he did now, he's looking at these dipolarization fronts, and he put arrows here to represent, I think these are the electron drift velocity, if I understand it correctly, and these different colors, green and blue, represent different magnetic topology associated with each of these structures. So the green means they're open flux rope, meaning they're connected to the solar wind, and these blue means they're connected to Mercury as closed magnetic field lines. Okay, the idea is he wanted to know which of these are truly so-called dipolarization fronts, which are flux ropes. And if you look from the side, you can see these clearly this different magnetic topology, these open field lines and flux rope, and these blue ones are closed field lines that are basically bombarding the inner magnetosphere of Mercury. Okay, so so once you have that identified, you can look at their evolution. So this is the way he likes to show this. You know, these green ones and are all moving downtail, and these blue ones are moving towards the planet. And this is the dichotomy where they diverge. And this is roughly the average X-line location Messenger had observed, 2.5 Mercury radii. And some of these diverging fronts start out as a flux row, but through reconnection with Mercury's magnetic field, it evolves into the so-called dipolarization fronts. By the time they get to this 1.5 Mercury radii, they all become so-called dipolarization fronts. They're all closed field lines without loop topology. And if you construct statistics of the currents of these structures, you see there's a clear down-dusk symmetry. Okay, things happen more often in this half compared to the other half. By the way, this is the dawn side, this is the dusk side. So I think in the simulation, at least from what we have seen so far, it reproduces that asymmetry fairly well. And our interpretation at the moment is that these structures are fairly small in terms of scale. They're on the scale somewhere in between electron and ion inertial scale. And once they're formed, they're going to be dominated by the motion of electron drift. And in this current sheet, the electrons naturally drift towards this side. Ions are drifting the other side. So we're thinking the main reason that we see that more often on one side is because they are tied to the electron flow, and the electrons are dragging them towards the downside, and that's where Messenger had seen a lot of these structures as a result of that. So we're still trying to do more careful analysis about the numbers, trying to calculate the electron drift velocity and compare that with the motion, the velocity these DFs are moving at, and try to get a more coherent story out of this. Okay. Now I only have about 5 minutes to talk about this part of my talk, and Ganymede, and this is a moon that shares a lot of similarities with Mercury in the sense that it's similar in size, but even larger than Mercury planet. It's the largest moon in our solar system, and is the only moon that we know that has an intrinsic magnetic field. So its internal field is even stronger than Mercury's. So it forms a magnetosphere, but the difference between Ganymede and Mercury is that Mercury is still embedded in the solar wind, which is supersonic and superaphanic. Right? The Mach number rarely goes below 1, but most likely is above 1. But at Ganymede, the ambient Jovian plasma flow, or sometimes called Jovian wind, comes at a subsonic and a subaphanic speed. So the Mach number here is most likely below half. So most of the time 0.3, 0.4 Mach number for the ambient Jovian flow. So there is no ball shock from in front of Ganymede's magnetosphere, and reconnection really is happening directly between the Jovian plasma and the unshocked Jovian plasma and Ganymede's magnetic field. Okay, and there is a lot of evidence observationally that tell us reconnection is active in this environment, and this basically presents us with a perfect example of so-called Dangji cycle convection. It really is Dangji cycle. The reconnection-driven convection is the dominant process that governs the structure of this tiny magnetosphere. Okay, and by the way, this magnetosphere is connected to the Jovian magnetosphere through field line currents and magnetic field lines. And there they create aurora footprint in the Jovian aurora, and it's observable, and it's showing up in many Hubble aurora images where you can see that bright spot from Ganymede. So we've done a lot of work, modeling work on Ganymede's magnetosphere as well. And so the thing I want to highlight here briefly is the effort, again, of using MHD epoch. We did that initially in 2016, where at the time we still use IPIC 3D to do the simulation, and you can tell the peak region has to follow a rectangular box shape. Okay, we used actually 4 boxes, okay, to cover the entire magnetopause, which is not as efficient as we can do now with flex. So 2 boxes upstream, downstream, and there are 2 boxes on the side to cover the magnetopause. Okay, so, and by the way, when you do the simulation, we run it usually coupled with Hall MHD. And this is the example I always like to show, is to kind of when you look at the reconnection structure, people often look at the exhaust coming out of the reconnection in terms of flow. And this is a comparison of the ion jets and the electron jets we get out of the PIC simulation. And they certainly show show up on different spatial scales. Okay, the ion outflow is accelerated to superharmonic speed much further away from the X line, and the electron jets showing up much closer to the X line region. And of course, that's because the different size of the diffusion region that these two species are having in our model. And I always thought this is a very nice demonstration of the importance of having a kinetic model handling the handling reconnection. One of my students a few years ago improved the simulation, and he did a lot of studies looking at the sensitivity of the simulation results on the grid resolution, number of cells you have, number of particles per cell you have, all kinds of things, and did a lot of validation of the model with observations. And this is one example where he compared simulation results with Galileo observations during one of the flybys, and you can see the agreement there is very good. He also looked at in detail how the distribution function evolves as function of distance from the X line and different parts of the X reconnection region. And these are the inflow region, and these are the separatrix, the outflow region in the associated with the X line. And there you can already see signs of crescent distribution, like this one example shown here, created by this meandering particles going across the boundary layer imposed by the magnetosphere. So I think between this example and the Mercury example I showed you, I think you can probably get a sense, the impression that the PIC model is able to give you a lot of useful output that you can diagnose and trying to understand some of the kinetic effects, physics that are happening in this relatively small size magnetosphere environment. And very recently, I say recently, it's already 2 years ago, I started doing some simulations for the recent Juno flyby. The Juno had passed Ganymede once during its extended mission, and using this latest capability. And this is, again, I was joking, this is more like a Lego design, all these Lego parts that I pile together to cover the magnetopause boundary. It's a very strange shape, but the shape follows the magnetopause of Ganymede. And we run this model and trying to see what's happening in the magnetotail. And again, if you look at the ion flows and the electron flows, and you see quite different structures. In the electron flows, you see relatively smaller structures, bursty nature of the reconnection happening over a large region in the magnetotail. And in the ion case, is fairly smooth and fairly quiescent, if you like, in this environment. And I think Juno, looking at the Juno trajectory, which is in green, it's right near the edge of seeing strong signatures of reconnection in the magnetotail. And I think this kind of a simulation is very useful in providing global context for interpreting the satellite observations, because it's always useful to know where you are relative to the critical regions in the magnetosphere. Okay, so this is the last slide I have for that Juno work is when Juno passed by the upstream magnetopause, our simulation predicted that it's likely that the spacecraft is going to encounter a FTE flux slope. You can tell here in this little tiny region when you cross the upstream magnetopause. And indeed, as soon as we made that presentation, a week later, the paper was published by the Juno team that talked about this. And yes, we see signatures of flux flow of FTEs only during the crossing of the upstream magnetopause Ganymede. So I think it was very nice confirmation of the capability we have now with the model. It really becomes a high fidelity tool for us to explore what's happening in the planetary environment. Okay, so I think with that, I want to conclude basically by saying that we have now moved beyond single fluid ideal MHD approach now in modeling planetary magnetospheres, pretty much enabled by this MHD EPIC tool that we have developed in the last 10 years. And I look forward to applying this to other environments. I started work for Saturn magnetospheres, and some days we're going to apply that to Uranus and get a better handle of reconnection happening on the magnetosphere boundary. Okay, with that, I will finish and I'm happy to take questions.
Excellent. Number of questions, but I'll defer to the floor first.
Hi, thanks for the nice talk. When you run these PIC simulations embedded in MHD, do you see a trend in the effects that you get with different proton to ion to electron mass ratios?
Yes, I think the answer definitely is yes. That's now I guess if you ask different people from our group, they may give you a slightly different answer, but I give you my perspective. The reason that we, in the Mercury simulations and in the Ganymede simulations that we have done so far, we sort of reside with this number 100. I was talking to Chris this morning. I think that's a good number that gives you a good separation between ion and the electron scales in a factor 10 in the initial scale. We have run simulations with numbers of 25 in the past, which really is small in the sense that the ion and electron scales become close to each other. And we feel the dynamics, the physics you get out of that may not be realistic enough, meaningful enough. So I always prefer to use as high of a number as possible, but always you have to do trade-off considering computational cost. At the moment, I think 100 seems to be a good number for most of our applications. But if you compare really 25, for example, and 100, you can certainly notice differences in the results.
So with the embedded PIC parts of the simulations, those VDFs are looking sufficiently deformed that they may generate waves. And it looks like you're resolving wave vectors that are probably the right scale to be able to actually see waves. Do you see ion or electron scale waves that are cropping up potentially driven by those VDFs, or is that something you haven't built the tools to look for yet?
It's largely the latter. We haven't really built a lot of tools looking into that, but that's really a great question and something that definitely we hope to pursue in the near future. Is yes, because if you're able to resolve the scales reasonably well, then you would expect in some scenarios you would expect to see the waves, and we do see some hints of that. For example, I think I remember some of the simulations we did for Mercury and for Ganymede, we see the lower hybrid drift instability, LDHI, lower hybrid LHDI waves in the simulation, and it has a very clear symptom, but we didn't really probe and analyze the wave properties in those simulations. But yeah, I think we may not resolve everything, but I think there are certain wave pairs that are being captured.
You're getting to 1/6 of a DE, and so you're probably going to capture a good chunk of it.
Yeah.
When you talk about like mass loading, charge exchange, like where does that come in the MHD and PIC simulations? Because like
good question.
Previously, like I've looked at PIC and it's like collisionless. So like, do you have to include like those like collisional processes?
Yeah, that's a very good question. So in the two examples I showed you today, none of these simulations had included mass loading. Naturally, because Mercury has a very tenuous exosphere at the best, and there is heavy ion, planetary ions coming from that exosphere that play a role, and then you could argue whether it's critical or not, but it does play a role in Mercury's magnetosphere. At the moment, we haven't included that. And for Ganymede, similarly, we do not include mass loading like we do for the Jovian and Saturnian simulations. But if I can answer a question, I can use the Jovian and Saturnian cases as the way to answer your question. So in those simulations, pretty much done within the MHD framework, we do add source and loss terms to the MHD continuity, momentum, and energy equations based on first principles, meaning you start out by calculating the ionization rates based on photoionization and electron impact. And those could be empirical, analytical way of prescribing ionization. And then we calculate charge exchange cross sections based on densities of neutrals and cross section area and relative velocity. So these are and recombination rate in a similar way based on electron temperature. So we do those source and loss term calculations, and then we add them correspondingly to the three equations that are being solved in the MHD framework. So that is done. Once you have that, the mass loading and the momentum loading are automatically included in our MHD simulation. Similar things we'll do for the cometary simulation as well, is you add those source and loss terms.
Thanks.
Thanks for your good talk. I have a question about the embedded PIC code. Does this code has a global simulation box like the image?
Does it have a global?
Simulation box is has large box like the MHP, or how it's work?
I'm not aware that we have tested the thing for the say to basically use the PIC to do entire global domain. I'm not aware that we've done that. Maybe I'll take it back. Okay, so the model can be actually set up. Maybe this is where you want to get to, I think, if I interpret your question correctly. Yes, we do. Okay, the Flex code we designed recently, unlike the IPIC3D, the IPIC3D, as you know, can run standalone. You can run IPIC3D as a standalone particle in cell code. The Flex code that we have developed locally cannot be run as a standalone code. It has to be coupled with our MHD. But with that said, if you say, I really want to do a local box simulation of turbulence reconnection, whatever you like, you can set up the model in this way. Say basically the PIC domain is the 99% of your simulation domain. And you have the MHD just within one grid cell larger than the PIC domain. So basically you use one grid cell from the MHD to do the coupling. You see what I mean? So you can basically put a large size PIC within the MHD domain and leave one cell for the coupling to happen. That you can run the Flex, and it's similar, it's largely equivalent to a standalone model, but the design we have, you have to run the MHD in parallel to the Flex model.
Okay.
Yeah.
So I see in the distributions of the electrons and the ions, there is more gaps in these distributions. So I am worried about the box size itself. So,
you mean the distributions?
Yes.
Are you referring to the examples I showed? Like,
yes.
Like this?
Yes.
So these distributions were collected within that bar, which is relatively big in this case. This was published 5 years ago. At that time, we could not afford a large number of particles, so that his sampling box is relatively large to collect sufficient statistics to construct these distributions. But if I go back to the Mercury example, here, we were able to use a smaller size sampling region, in this case a sphere, to get sufficient amount of statistics to construct distribution function. So it's a matter of how many macro particles we can afford running. And that basically dictates how big a sampling region you could realistically use to extract particle information.
Thank you.
Do you have any issue with like edge effects at the boundary between like the PIC simulation and the MHD, or is that kind of minor?
Yes, we sometimes do run into those issues. I think I was talking to Chris this morning also about this problem. Is yes, the idea. Maybe this is a good example. I don't know. Maybe this is not. Sometimes I have figures to show when you take out this boundary, would you be able to notice where the peak coupling is happening? And sometimes you cannot tell. Things are coupled very smoothly. So a general principle I always have in mind is because we know the MHD and the peak codes they contain totally or largely different physics. One is a fluid treatment, the other is kinetic treatment. And they do have mismatch in that regard. So the idea is if you have a too small of a peak domain, by the time the particle distributions that have reached the boundary of the peak domain, if they're largely non-Maxwellian, they deviate from Maxwellian dramatically, then you will potentially have a hard time of reconciling at the boundaries between MHD and peak. Right? I think the very natural result, you get a very different particle distributions assumed by the peak and by the MHD. So it would be beneficial if you could afford, if possible, you would want your peak domain to extend a little further away from that place, such that at the boundaries when we couple, the distributions are largely have become Maxwellian. And in that case, we see our coupling works very, very well, very smoothly. You almost cannot tell there is a boundary between a particle in cell code and MHD. But if you make it too small, like say, oh, I want to save time, I only want to put a peak box here. Run a simulation, and it's almost a guarantee you're going to see artifacts very clearly. You know, the mismatch will show up immediately when you have a too small of a peak domain. But I think the way that's actually one of the motivations we want to go with the flex model is we know that it's happening a lot of times. And so we want to place the peak strategically such that you can use your computational resource in regions that are really needed. Okay. And you can afford, imagine previously if you only can use a box and you're using your box to cover regions that are not really that useful and not really containing a lot of kinetic effects, and that's a quote unquote waste of computational resource. And now, by using this curved boundary, we are able to kind of use whatever we have now, affordable resource to capture regions that are critical in terms of kinetic effects, and then also making sure the transition between peak and MHD happens in a very smooth way.
Thank you.
Excellent. Well, let's thank the speaker again.
Okay, thank you.